Okay, let's get started. So today we're going to talk about networks. And before I get started, any questions? No? Okay, so a quick reminder, we have our final project due this week. So, and then there will be office hours today up until Friday. And please also get in touch with your mentoring TA if your team has any questions or concerns. But yeah, we are getting close to the end of the semester and I'm excited to see what the project might be. Okay, so today we're going to talk about networks. Again, networks by itself is it's a topic that could cover an entire semester of material. So we're going to give a very high level. A lot of the network science stuff is related to graph and graph theory. Okay, so we're going to introduce some of those concepts and a few of those most popular algorithms, and then we're going to move on to the Jupyter Notebook. Okay, so there's many applications of graphs, but if you think about the application of graphs, there goes into sort of things like path planning, things like social networks, things like circuitry planning, and things like your daily search, which is based on PageRank. That is in some form can be considered as a graph algorithm. So, in some sense that our current social network essentially run on those graph data structures. So, of course, the most widely used one is Facebook, where you can imagine each node is a user, and then the connection if they're friends with each other, or if you think about Twitter, there's a connection if one follows another. There's also things like biological networks, which looks at interaction between genes, proteins, and chemical product. There's also sort of brain networks, specifically talking about connection between neurons. There's also, if you think about your ancestry, your phylogenomic, the evolutionary tree or phylogeny, that is sort of, evolution of life can be also be mapped as a form of a network or tree structure. This is an example of a sort of a biological network. And if you can sort of zoom in, it's a kind of looking at the interaction between different chemical compounds in a biological system. So I put here a link to a very interesting sort of TED talk, if you are into TED. And then there is this talk about the hidden influence of the social network, where the speaker discussed about a variety of traits, such as happiness or obesity, can spread from person to person. And this is performed through social network analysis. So here's a link. I would highly recommend you to kind of, watch this over your, I don't know, lunch break or something. It's a fun watch. Now, today, our focus is over some foundations over graph theory and a few very commonly used graph algorithms. So, for folks who are computer science major, usually there is an entire chapter of the textbook that is dedicated to graph theory and graph algorithms. But here, I'm just going to give you the ones that is most commonly used, for example, for a data scientist. So whenever we talk about graphs, there's actually a specific type of graphs. And I just showed a few pictures here. There is the first type, which is a tree structure. And tree, by definition, is a situation where between any two nodes, there is a unique path between them, okay? Another way to describe what is a tree is that there is no loop in a tree. Right, so if I add this connection right here, this is no longer a tree. And also we can have the generic network, which typically when we talk about network, we consider as a graph. It has sort of, one way people describe it is it has a set of nodes and a set of edges. So in this case, our visualization, this one has 7 nodes and it has multiple edges that connect them. There's also the definition of hypergraph. Well, the edge should really come here. Hypergraph, which is in a sense of a generalization of a graph. The idea of a hypergraph, if I were going to denote hypergraph, it has a set, the set X would be the set of nodes as before, but Y is really a set of sets where each element in Y is a subset of the nodes. So in this case, for example, this is an element in Y which contains 4 nodes, which is called a hyperedge. This is another hyperedge that contains those 2, and those 2 hyperedge has non-empty intersection. So there's a recent trend actually in graph analysis to move from a graph perspective into a hypergraph perspective. So, you know, for example, if you actually think about social network, people typically model social network as a graph, but in fact, it doesn't have to be a graph. It can be a hypergraph, because you can think about people who are in, say, a particular sort of a club, for example, then everybody in that particular social club form a hyperedge. Among the graph, there's a very specific type of graph called bipartite graph. And then the idea is the nodes can be partitioned into 2 parts, where among themselves, there's no edges. And the edges only exist between those 2 partitions. So only from the rectangle to the circular node, but not among the rectangle or among the circle. So this type of bipartite graph will arise in specific data situations. So of course, whenever we talk about graph theory, we always talk about the origin of graph theory. This is arguably also the origin of topology. So the idea is, you know, this problem from the, you know, the 1736, which is there's a city and you know, there's a piece of land and there's an island, and then there's this sort of you know, 7 different bridges. So the question is that, can you kind of take a walk to visit every landmass without crossing the bridge twice? So, you know, if I kind of walk like this, can I do that? And then the way to kind of solve this problem is resulting in some sort of abstraction. And what is a specific abstraction? Is that every piece of land is now represented by a node. So for example, this piece of land is a node here, this is another node, this is another node, and so on. And then if there is sort of an edge connecting them, for example, you know, from the island, let's say this is node A right here. If there is there's a bridge that connecting the land with another piece of land, there's an edge between them. And then the idea is, you know, can you kind of go through all the land without passing through the edges more than once? And the way to solve this problem is that this is only possible if the underlying graph have at least 2 nodes with odd number of links. And this one actually have 4 nodes with odd number of links. So the answer is no. So this is sort of the birth of essentially the graph theory. And you can actually play with this. And I'm not going to go into the proof. There's actually a very simple proof of this if you go through things like 2100, the discrete structure course. But this is idea of abstraction is give birth to the graph theory. The abstraction, it happens is that every single piece of land between a node and every piece of edge between every single piece of bridge became an edge connecting land masses. Okay, so there's a lot of terminologies that is used in graph theory, and we're going to visit some of them. If you have a graph G, it consists of a set of vertices V, which sometimes also called nodes, and a set of edges, which sometimes is called links connecting those vertices. So those are vertices and those are edges. And sometimes people use the word graph and network interchangeably. And I have a specific preference when I'm talking about something very abstract, I use the word graph. And if I talk about something that arises from data, I call them networks. But you know, most people kind of use this interchangeably. Now, there is the concept of a simple graph. A simple graph is a graph that has no multiple edges and no loops. So of course, this picture on the right is not a simple graph because it has self loops, which is this orange curve right here, it also has multiple edges between some nodes. So if you think about abstraction between cities in United States, so say this is Salt Lake City, this is say Provo, and there is sort of the I-15 that connect them, but you can also take some sort of back roads that also connect them. So if you do abstraction, the sort of road network is not necessarily a simple graph if you want to preserve all the roads. But if you only focus on highway, maybe you're getting closer to be something simple. But this is a case where there's multiple edges connecting nodes. All right. So of course, there's also things like direction. What is a directed graph? For example, I have node A, node B, node C, and where each of this node represent a web page, and the arrow represent whether this web page contain a link that links to B. So if you think about the world of all web pages that is out there, there may be like multiple edges. So A is linked to B, and B is linked back to A. A is linked to B, B is linked to C, C is linked to D, and maybe D and A also is sort of linked with one another. So in some sense that today we're actually going to talk about the very simple form of PageRank. The PageRank is really rely on sort of the direction at what page is pointing to what. And then the idea is to assign importance to the page if there's many pages linked to it and whether it's linked to many pages. So the importance is how influential a particular web page is when you actually rank the web pages. Okay. So now remember, I kind of gave a quick introduction of a hypergraph. It's sort of like a generalization of graph where the edge connect multiple vertices. So another way to think about it is that it's really a hypergraph is a set of sets. So let's say 1, 2, 3, 4, 5, 6, 7. Let's say 8, 9, and so on and so forth. Let's say 11, 12. Those are node IDs. Then the hypergraphs, remember I'm using this notation. Then my X is all the nodes 1, 2, 3, 4, and my hyper edges are each hyper edge is a set of vertices. So for example, this hyper edge right here is a set of vertices 1, 2, 3, 4, and then this hyper edge here is a set of vertices 11, 12, and so on. Right? I didn't spell it out completely, but you get the picture. And the hypergraph actually arise quite frequently. For example, hypergraph arise in also in biological network where each of the node is a particular gene, and each of the hyper edge is what's called biological pathway that those genes participate in. Another form of hypergraph where you can see is called co-author network, where let's say multiple people write the same research paper together. Then let's say a particular author is represented by a hyper edge, and its node are all the people who has co-authored at least one paper with this particular person. That would be a mapping of hypergraph as well. So as I mentioned before, there is actually an upward trend of people doing data analysis involving hypergraph. There's also some other content is that if I have a graph that has no edge, we kind of call it independent set. Or if we have a graph that contains all the possible edge, this is called a clique, right? So, this is a clique involving a large number, but a typical clique, you can think about this is also a clique where every node is connected to every other node. There's also what's called unconnected graph and connected graph. Of course, unconnected graph is basically if I start with a particular node in the graph, for example, here, I cannot reach all the other vertices. So for example, from here, I can reach all those vertices, but it cannot reach vertices here because the graph is disconnected. So it has multiple components. Of course, the connected graph is opposite, where for any nodes, you can reach any nodes from any starting node. So that's why the graph is connected. There's something called a deculation point. And specifically, and we're going to see that in our Jupyter notebook too, is that a node can be considered being important because once you remove it, it disconnect the graph. For example, this red node right here is an articulation point, because if I actually remove this, the underlying graph is going to be disconnected into a component here and a component here. Okay. So in a way, you can think about, well, articulation point. What is the best example is that, you kind of think about if you have an island connected to the mainland, and if you through a bridge, if you break any points on the bridge, you kind of disconnect the island from the mainland. So it can kind of indicate a little bit importance of this node. But there's other ways of measuring importance of a node in a graph. All right. Okay, so there's also a more deeply, I already introduced the definition of a bipartite graph, which means that I can partition the nodes into two sets, such that among each set themselves, there's no edges, but the edges only exist between. But bipartite graph sometimes can be misleading due to its visualization. If I visualize on the right-hand side, you're like, oh, clearly this is a bipartite graph because I can partition the nodes into two sets. But on the left, I would argue this is also a bipartite graph. In fact, what's happened is that all the square node is on one side and all the circle node is on the other. So in a way that you can draw this bipartite graph on the left as a graph on the right, I put the square on the left and circle on the right. Okay. So a biconnected graph is a graph without articulation point. So for example, in the previous example, remember this node is an articulation point because once I disconnect the graph into two components. But here, remember here, I added extra edge right here. So even if I disconnect here, the graph remains connected. So in a way that there's no articulation points, there's no a single point that, in some sense, disconnect, its removal disconnect the network. So if you think about biconnectiveness, why is a useful property? It actually shows a little bit over the robustness of the underlying graph data. For example, assuming this is my transportation network, if this is a particular bridge and this bridge is sort of like collapsed, or it's like there's a traffic jam or there's an accident, it's not accessible, a biconnected graph will enable you have alternative route to reach your destination. Okay, so we also discussed what is a tree. A tree is a graph that has no cycle. Another way that whenever people think about a tree, there is a way of choosing what's called a root node. If I visualize the tree like this, it's very obvious this is a root and then this is a leaf. But sometimes you can actually define, even in here, I can choose this to be the root, I can choose this to be root. Depending on how you choose a root, you can actually resort the nodes in the tree by the level and so on. Okay, so we're going to see some tree structure later when we talk about, well, actually also graph structure. But the tree is a very specific type of data structure that is used a lot in computer science. So there's also things like an order tree versus, like order tree, meaning that, there's a specific ordering of the underlying node. For example, in this case, I have A, B, C, D that is order my node by sort of the level. This is the first level, this is second level, this is the third level. And then if that's the case, if I have to have this order or this label, those are two different types of tree because the label is actually different. Okay. And also because of the label, it is sort of different. For example, you can actually differentiate them. Now, the one other important component is actually called node degree. The node degree is the number of edges that is connected to a node. All right. And then, of course, when your underlying graph is directed, then the degree sometimes is called in degree versus out degree, depends on the direction of the edges that's come out of it. So for example, in this particular example, node 2 has degree 3 because it has 3 neighbors. And then you can also compute what's called the average degree, which is essentially taking all the degrees, sum them all together, and divided by the number of nodes. Okay, and then you can also plot things like degree distribution and so on. So for example, in this circle graph, everybody has a degree 2. So the histogram of degree distribution looks like there's only 1 bar because everybody is a degree 2. So of course, one of the sort of more recent advances, when I say recent, is mostly for the past 20 years or so, when people study sort of real networks. And it turns out in real networks, it kind of follows sort of what's called a power law degree distribution, meaning that, again, this x-axis is the degree, and then the y-axis is a percentage of nodes that has that degree. So it has a sort of like a shape like this, meaning that there's only a few nodes that has a really high degree. And this apparently is quite a common phenomenon for real world social network, for example, that maybe there's a small number of people who's extremely influential, and then they are sort of the tail end of the distribution, but most of the distribution follow in a shape like this. Okay, that is what happened in a real network. So in a lot of cases, that other means that there's a very large number of nodes that has a very small number of degree. So again, one way to think about importance is measuring the importance of a node based on its degree. So for example, again, in social networks, let's say somebody's Instagram account, there's a link between them if there one follows another. So the one that has a lot of followers are the ones that is in some sense considered important. They are the important social influencers in Instagram social network. Yeah. So in this case, and this is we can duplicate these results through Jupyter Notebook. This is a social network come from the Hugo's novel, and then this is if I kind of change the size of the node by its degree, this is a sort of an important character in the novel. So the next thing, another way of measure sort of importance is what's called betweenness centrality. It's a measure of how many shortest paths pass through a node, and a good measure for the overall relevance of a node in a graph. So again, we're going to look at the mathematical definition very soon. But the idea is, again, because this is sort of a central node, to go from any other node to any other node, it's very likely to pass through this node. So if you count the number of shortest paths that pass through this node, the higher, the better. Another way of thinking about centrality is essentially think about it as a business hub, right? So if you think about Salt Lake City as a Salt Lake City airport, it's actually going to have a pretty high centrality because a lot of flights transfer here. So to go from West Coast to East Coast, East Coast to West Coast, some of those paths have to pass through Salt Lake City. So there's a large number of shortest paths going through here, and then it has a high betweenness centrality. Okay, so of course, in terms of betweenness centrality, you can also look at the distribution. In the same data we showed before, you can see the degree distribution where it follows something like this, but betweenness centrality kind of highlights some of the other nodes that is important. But in this particular case, it's possible in this specific case, the one that has high degree also have the high betweenness centrality, but they're not exactly the same measure, okay? And specifically, actually, if you think about those cases where you can have a node that has a very low degree, okay? So this is sort of example why they are different. If I look at node A, the node A degree is actually very small. It has a degree of 2, but it actually will have a very high centrality because for any nodes on the left, in order to go to the right, it has to pass through, let's say. So the centrality is actually quite high, right? Okay. All right, so another way when you actually store the graphs, sometimes it's stored as adjacency matrix. So what do I mean by that is that the nodes are represented as rows and columns. So in this specific case, let's say this is undirected graph. I have node 1, 2, 3, and 4. So what I do is I say, well, node 1, 2, 3, 4, node 1, 2, 3, 4. Is 1 and 2 connected? Yes, so there's a 1. Is 1 and 3 connected? Yes, there's a 1. Is 1 and 4 connected? No, there's a 0. So this is just adjacency matrix. But of course, the directed network is slightly different let's say again, I have 1, 2, 3, 4, 1, 2, 3, 4. Let's see, did I get it other way around? Okay, so I can say, well, in this particular case, maybe I should resort it. I want to say, is 3 reachable, or is 1 reachable by 3? The answer is yes, and that's the only one that is reachable. Is 1 reachable by 3? The answer is yes. Is 2 reachable by 1? The answer is yes. Is 2 reachable by 3? The answer is yes. But 2 is not reachable by 4 because 4 does not have this edge. Okay. So there is an interesting sort of things when you actually represent graph data as adjacency matrix is that when the network is undirected, this adjacency matrix here is symmetric, meaning that there's a diagonal here, and then it's a reflection from one side to another, meaning that if 1 and 3 are connected, then 3 and 1 are connected. But in the directed situation, if 1 and 3 are connected, it does not guarantee 3 and 1 are connected because there's a directional thing right here. Okay. There's also what's called path and distance. A path is a route along the edges. And then the length is the number of edges that you kind of incur. And then the diameter is the longest, shortest path. It's a little bit tricky to understand what it means, the longest or shortest path. It's essentially looking at for every single node, what is the shortest path between this node to everybody else, and choose the longest one. And then you do this for every single node. Okay. So for example, in this case, if I want to go from node 1 to node 6 in the undirected case, I can go from here, and then this is a path of 1, 2, 3, 4, 5 is a path of length 5. But I can also go from here, and this path has a length 3. So this is the shortest path between 1 and 6. Okay. And similarly, between 1 and 7, I can go here versus I can go here. This is actually, there's 2 shortest paths. Each of those paths is of length 3. So whenever we talk about shortest paths, it's not guaranteed to be unique, right? The only time where the shortest path is guaranteed to be unique is that when your data is a tree. When you have a tree, the shortest path between any 2 nodes is unique. Okay. Actually, the path between any 2 nodes is unique. Okay, so let's do a little bit computation. So I know today which we're going to talk about a combination between mathematical definition, algorithms, and code. So let's talk about betweenness centrality in the current example. So the mathematical formulation of betweenness centrality, let's say I'm going to focus on a particular node E. I want to compute betweenness centrality for E. It's the number of sort of shortest paths that pass through it divided by all possible paths. So the way I'm going to compute this is as follows. I'm going to look at how many shortest paths are there between a pair of nodes, let's say AB, and I'm going to see how many of those shortest paths pass through E. So the number of shortest paths between A and B, there's only one path. So the number of shortest paths is 1. But this shortest path does not go through E. So the number of shortest path that goes through E is 0. Okay, so the first term here is the number of shortest paths between A, B that goes through E. And then this is the total number of shortest paths between those 2 nodes. Now, between A and C, can somebody tell me how many shortest paths are there between A and C? Somebody's talking, I couldn't hear, or you can type. So the number of shortest paths between A and C is 1, okay? But this shortest path does not, yes, so people says, oh, typo, okay. The number of shortest paths between A and C is 1, but this shortest path also does not pass through E, so it's 0 that contains E. Same thing, how long is the shortest path between A and D? How many shortest paths are there between A and D? It's 1, right? It's basically here, and it does not pass through E. So again, it's 0. This is where things become interesting. When I'm doing shortest paths between A and F, I can go here. This path has a length of 4, but I can also go through here. This also path has length 4. So the number of shortest paths to go from A to F is actually 2. And then one of them contains node E. Okay, so this is the first time things become interesting. We can also do, again, BC, which is 0, 1, BD is 0, 1, and now it's BF. BF, again, going from B to F, you have this path, you have this path, both of them of a length F, so it has 2 paths, and one of them contains E. Same thing with CD is 0, 1, and CF, again, CF is the one that goes through here and goes through here. So their shortest path is 2, there's one path that contains E, and then DF is 0, 1, okay? So now what's happened is that those are the 3 cases. I'm going to sum them all together over this quotient. So I sum them together. This is 0.5, 0.5, 0.5. And then this shortest path is 1.5. Sorry, the centrality is 1.5 for node E. Okay, so let's switch to, let's now switch to Jupyter Notebook. Let's look at how we actually compute this. Okay. So I cover some of those definitions already. So in the Jupyter Notebook, when we actually play with networks, there's a library called NetworkX. The way to use it is just import NetworkX as NX. Okay, so let's have some initial setup. And one thing we can do for a NetworkX is that you can sort of define a graph. So I'm going to initialize a graph. This graph is an author's graph, and I'm going to put a bunch of names. And so when I say add node, add node, add node, I'm just adding the name of the author in this graph. So this is a graph. Think about this graph where each node is an author, and then there's an edge between them if they have written a paper together. So in some sense, I'm going to add edges between Alex and Mark, between Mark and Wolfgang, and between Mark and Helwig. And then those are actually people in visualization. Alex is our own faculty, but the other people are people who works in data visualization. And then I can, oh, actually, let me hide my output. Reloaded. Okay, so now I can do print and then just list the author.nodes. Remember, authors is the name of my graph. I just add a bunch of nodes and a bunch of edges. So I'm just displaying what are the nodes, which are the author names, and then edges are the edges connecting 2 nodes. So that's precisely how I defined my data to be. So now what I'm going to do is I can take this graph, which is the author's graph. I can add edges. And when I add edges, there are some nodes that wasn't there, but when I add edges, it will actually add the nodes again. So if I do this, if you see that, originally there's 4 nodes, now there's 5 nodes. So actually we kind of added another author who's a faculty, I believe in Harvard, and Hans Peter is now added as a new node. And then same thing with the 2 edges that's being added is now added to this graph. The other thing that is really useful is that not only you have node and edges, you can also have things like attributes. And when you talk about attributes, this is essentially, things that is attached to each of this node. For example, in this specific case, I kind of want to define for each node, I want to give it a field called institution, and I want to assign value to that field. So in this specific case, I'm going to say, well, Hans Peter is a faculty at Harvard, Alex is a faculty at U of U, and Mark is a faculty at JKU, and so on and so forth. And I add this attribute. And now if I actually display, when I say get node attribute for the authors, and under the field institution, it's going to display what is the node name, what is the value of institution, the name and the value of the institution, and so on. Remember, the institution doesn't have to be a single institution. It can be sort of like an array of multiple institutions or a list. Okay, so, and we can access sort of individual, nodes. In this particular case, when I say data is equal to true, I kind of want to look at what is being stored in my data. remember I assigned institution to some subset of the node. So when I display the attribute, it says, okay, Alex institution U of U. But also there is people where I did not assign the attribute. So the corresponding attribute, the field and attributes are actually empty set, and that's okay. And also we can query specific node attributes. For example, give me the nodes Mark. Remember, Mark has attributes of institution, and the value is those two institutions. And if I actually do authors just by looking at the Mark, the node's ID, it actually returns the neighbor of this node. Okay. Now, how do we visualize a graph? This is, again, comes together with Network X. Well, it's not the best graph visualization library out there, but it's the easiest one we can demonstrate through Jupyter Notebooks. That's what we're doing. So in this particular case, I am going to use what's called a spring layout. The way spring layout works is that it's assumed that for the nodes, assume that there is a spring between them. And then the spring has sort of attractive and repulsive forces. And then the visualization is basically trying to find an equilibrium of this. So this is how the visualization looks like. For the data set we just described, there's 5 authors, there's edge between them. Of course, this shows connectivity or topology of the underlying graph, but it doesn't really show the attributes. So you want to kind of, well, I mean, it doesn't even show the name of the node. So we want to add the label. So in this case, right, we first compute the layout, and then I'm going to specify the size of the node. And then we're going to sort of draw a network with label, where the label coming from the graph itself. And now if I do that, you can see that now I have visualized this network with author names attached to it, to each of the node. But you can also use a slightly different visualization. And then this is what's called a shell layout. And then the idea is that the nodes are on sort of try to place it on a circle or ellipsoid as much as possible. And that's what you have. So there's a lot of different graph layout algorithms out there. The most commonly used one are things like spring layout or force direct layout. The idea is very similar. In the force direct layout, you have 2 nodes. There's attractive force and repulsive force. And then the final layout happens when you actually achieve an equilibrium of those forces. And then usually it will give you something fairly pleasant to look at for small graphs. Okay, so now for Network X, you can also get information or statistics. So .info is tell you this graph has 5 nodes and 6 edges. And remember, we just talked about degree, then we can actually return the degree. The degree view says the node Alex has degree 3. Why? If you actually look at this, there's 3 edges that is coming out of it. So it has 3 neighbors. You can also visualize the degree as a size of the node. So again, remember we said degree might be an importance measure for a network. So we can probably resize it based on its degree. So again, in this specific case, I'm going to sort of draw the network with label, but the node size is proportional to the weights, where weights is coming from the actual degree. So in this specific case, this function takes some weights and resize the nodes based on the weights. When I call this function, I'm going to basically append the degree times some large number. So when I do that, I'm going to the scale degree is essentially how large I want it to be proportional to the degree. Wait, what did I do? Oh, I forgot to run this, of course. So now you see that, you know, the Wolfgang is the one with a small degree. So when you draw it, this node is much smaller. You can also do histogram. Remember, you know, I can do, when I collect a degree, is essentially degree of each one. And then I can collect the degree, and then I can draw a histogram of this degree. And then that shows, you know, in this particular network, remember, you know, all this node, you know, Alex has degree 3, Helwig has degree 3, Hans Peter and Mark, oh, Mark also has degree 3, Hans Peter has degree 2, Wolfgang has degree 1. So this is sort of like a histogram distribution of the degree. So when we actually are talking about dealing with graphs, the graphs have different kind of format. And specifically, what we are going to use is called this GML format. Of course, there's also JSON format and so on and so forth. So in this GML format specifies, okay, I specify I'm dealing with a graph. And for each of this node, it has an ID and it has a label, right? So node 0, ID 0 has a label of a particular person. In the Hugo's novel, and this is another label with a person's name and so on and so forth. That specifies the name as the edge, as a node, and then I'm going to specify the edge, which talks about what is the source and then the target of it. Okay, so in this case, this is already specified in our folder, so I'm just going to note it directly, and I'm going to display it. And when I say display dot nodes, this specific graph that is read into the file, what we do is it shows essentially the name of the characters in the novel. And then we can also print other information. It says, well, in the specific social network from Hugo's novel, there are 77 nodes and 254 edges. And I can actually drew them as before. This is again drew them with drew this network with labels, and this is what you get. Okay, so this it's, in some sense this shows the social interaction, the interaction network of characters in the novel. So remember we talk about sort of between its centrality and so on. Those come with the library, but first of all, we want to actually plot the nodes with some weights. So this is just a function that takes certain weights in the graph. Again, kind of drew the graph where the nodes is sort of proportional to this weight. So the first one, when we say something is important, is using degree. So in this particular case, I'm going to use a degree to redraw the graph so that the more higher degree nodes is bigger. So this was, first of all, let's look at the degree. This first character here is the one that is most important. If you ever read the book, this one has a degree of 36. So if you actually drew it, you actually see that it's right here where my mouse is. This one has the largest degree, and it's sort of highlighted in my visualization to say this is an important player in this novel. But remember, we just went through an example of betweenness centrality, and let's just look at how it runs. This is exactly the same example as I showed you before, where I have this A, B, C, D, E, F, D. And remember, we computed this betweenness centrality of E. Well, it turns out network X has an algorithm that already computed, so you don't have to compute it from scratch. That's what you see right here. And again, you can draw this network. This is a network we kind of saw before. And this is showing sort of betweenness centrality with respect to different nodes. So in this case, the node C actually has a highest centrality versus node E has a centrality of 1.5, which is what we computed earlier. Not surprising, because remember, if I C is sort of, think about it as an important hub in this neural network, or sorry, in this network. And then what happened also, if you remove C, is actually also disconnect the underlying graph. Okay. So now let's plot the betweenness centrality for the Nesmith novel as well. Again, the one that has the highest degree also happen to have the highest betweenness centrality. And again, I'm going to visualize it. You see that this one is actually the one that has highest, largest node. It happened to have the highest degree, but it also has the highest centrality. But what's really interesting, I want to kind of compare those two, is that you can have multiple nodes in this picture that has a really high degree. But if you're actually thinking about centrality, there's actually much fewer nodes. So those are essentially like the ones that plays important roles in terms of how to connect in different plots of the novel. All right. Now let's move on to the most simple version of PageRank. Of course, PageRank has been around for a number of years, and it's used for rank the web pages on the internet, and then the ones that has a high page rank, assuming you are below the advertisement web pages, the one that has a higher page rank is going to show up earlier in your search result. The assumption is basically more important website are likely to receive more links from other websites. So in a way that think about, all the other websites that link to the current website kind of contribute towards its importance. So it's a little bit roundabout way. It's kind of start by doing some sort of diffusion, and we're going to run a very simple algorithm on my slides to showcase this. Then it's actually a fairly fun example. So let's do that together before we see the actual code. All right, so let's do PageRank by hand. All right, so how do we do that? Well, assuming I can share my screen. Okay, so I'm going to do a very simple PageRank illustration. We have a network here where A goes to D, it's directed. So, there's a page D that A is point to, and page D is also B point to and D point to. Important part is that both B and D are point to each other, okay? And what we're going to do is we're going to start at step 0. I'm going to start by having a uniform mass over each one of them. There's 4 nodes, so let's say each one of them has a quarter of the mass. Okay, then what's the next step? I'm going to start from A, okay? So because A has a link to D, so what I'm going to do is I am going to transfer, let's see, let me make sure I'm doing the right thing. Yes. I really want to make sure I'm doing the right order. Yes, this is the right order. So what I'm going to do, I'm going to actually use a different color. Okay, I'm going to do is that because A goes to D, so whatever amount of mass that is over A is now transferred to D. So this is what I'm going to do. D is now 0.25 and A became 0. All right. Now I'm going to move on to B. B goes to D and goes to C. Because it's 2 outgoing, so the mass is split between those 2. So what B goes is to say, well, it goes to D with a 0.125. It also goes to C, so C has 0.125. And now B became 0, okay? So this is essentially the first, well, I'm not completely done yet. So now let's move on to onto C. C goes to D. So whatever is C in mass in C is going to translate to D. So whatever mass over C goes into D. And then I'm going to move into, so this is now become 0. And now I'm going to on D, where D goes to. D is connected to B. So whatever used to be at D is 0.25 is now transferred back to B. So now this is my step 1. So what you see on this step 1 is that the mass gets redistributed, depends on how the edges are pushed forward. And what you can see, like at the end of this day, this is 0.625. At least at this iteration, my node D got the most importance measure among everybody else because it has most of those inward links. But that is the first iteration. I can also continue with the iteration B, next iteration, because A no longer have any mass, so I'm just going to ignore this. Again, I'm going to start with B. B has mass again. Oh, sorry, I need to correct myself. The B's mass is actually 0.25, yes. So B's mass now goes to C and D. So you can redistribute and sort of iterate my process. And what you end up getting, if you want to challenge yourself, you will end up getting in the next iteration, you will get something like this. And the idea of PageRank is to keep running this sort of mass redistribution until it converges, okay? And then at the end of the day, once it converges, the one with the highest mass is the one with the highest PageRank. Any questions? Okay, there's a question. Yes.
If we look at BN, they are mostly having, after second iteration, BN, they are having mostly same. Right, but if you see in the picture, BN having more.
Right. So what I'm showing is sort of the result after the first iteration, after second iteration, and so on. So the importance part here is that when I'm going through the first step, right, I'm looking at the current mass distribution, right? So what happened is that, let's say at D, when D is accumulating this, but D originally have this much of mass, and D is connected to B, that's why B always takes over and take the mass at the very end of the day. So that's why when I say I challenge yourself is the next iteration, because D and B are always connected, B is actually going to carry over what D have. So in a way that in this particular case, B and D actually influence each other as you go along with the iteration. But I have to say that in some case that D is actually still has a little bit more influence because it has, you know, another way to actually think about it, what's really interesting about this. What if I remove this node? Okay, what is on the line? They just sort of translate into each other. And then the equilibrium is that everybody is equally important. But because of A, kind of break out the imbalance. Does that make sense? Let's look at how this runs in our algorithm, okay? It turns out PageRank is part of network X, so you don't have to code it from scratch. And to be fair, what's in the network X is implementation is slightly different than the simplified version I'm showing you here. So this is exactly same picture I just drew, okay? And then I am going to show the picture. And then this is what this is exactly the same example I just drew by hand. And if you look at here, I said ABCD originally has 0.25, okay? And after one iteration, A is 0, B is 0.25, C is 0.125, and 6 is 0.625. And the next iteration, B is carry over 0.625, C is 1.5, and D is 0.25, and so on. So you can repeat this process and see until it converges. It takes a little bit while to balance out. So I didn't go by hand. You know, if you go further, you see B is 0.25, D is 0.43, and B is 0.43, D is 0.43, and B is 0.43. So it goes back and forth a little bit until it finally kind of converge. And in this specific case, what's interesting is actually, you can see there's actually a, let's see what might be. It actually B is somewhat more, slightly more important than D in the implementation that is part of network X. Okay. Oh, sorry. Let me put it this way. Sorry. Let me correct myself. This is the algorithm I just did. This is my simple algorithm. And then the network X implementation is slightly different. So if you actually look at network X, D is very close to B. When I terminate, D is slightly more than, B is slightly more than D. But in the networks X implementation, they are roughly the same between these two. Okay. But what's really interesting is that somehow C doesn't benefit because of A. It's like A kind of break off the balance. And you're right to some degree that, you know, essentially because there is a bi-direction saying whatever D is always going to try to influence B and B is trying to influence D. So at the end of equilibrium, in the implementation, there's only a minor difference between these two nodes. And then there is something called a damping factor in the implementation. And then this is kind of interesting. So essentially, the damping thing is that sometimes when you actually, when people are clicking, there is the idea of people actually, randomly clicking the links. The idea of sort of stopping is at some point, I'm going to stop my iteration, and that iteration probability is 1 minus alpha. So when alpha is really big, I want to kind of run this for a longer period of time. But when it's really small, it's going to be closer to the initial distribution. So if I set it to be 0.85, you see that this is closer to what we are converging in this specific case. Actually, in this case, B actually has a smaller mass than D. All right, this is just to say, oh, I think I'm roughly close, I'm going to stop. But if I change it to be, say, 1.15, what you see that this is actually very closer to the initialization of my original thing. So as you change this damping factor, it kind of controls when do you actually stop this iteration. So the page rank was designed for directed graph, as in my example. But in NetworkX, when you have an undirected graph, you can basically treat the undirected graph and each edge to be a double arrow, okay? And you can do the same thing with the novel data set that we are talking about before. And again, what's interesting is the one that we deem to be important, which has a high degree, high centrality, also has a pretty high page rank. Okay, so another way, if I can visualize it, this is how this sort of, where did it go? It should be somewhere here, like right here. That is the one proportional to its page rank. So in some sense, the page rank actually align well also with our intuition of the importance of nodes. Okay. Okay, so now let's do a little bit comparison since we're already here. We want to talk about degree and histogram of degree. So, well, not histogram, just like number of the degree distribution. This is the degree, and then here's the histogram. But if you actually do centrality, you get a slightly different distribution. In fact, there's a lot less nodes that has high centrality. And then finally, if you do page rank, it's actually kind of has a very, slightly in between, as not as sharp as the centrality distribution, but is a slightly different distribution than the actual degree. Okay. So the next thing I want to talk about is when you remove nodes. Okay. So you can take my novel social network and remove a particular player. When I do that, when I say remove this node, when I do that, it's actually, oh, that's not what I want to do. It actually changes, you recompute the centrality. Because I remove the most highly central nodes, I now have a new most important one after removal. But if I actually visualize it, this turns out because this is the one that is most important, it's actually disconnected the underlying graph into 1, 2, 3, 4, 5, 6, 7. It's actually disconnected the social network into 7 connected components. Okay. And if I actually want to know how many components are there, we can call number of connected components, and it's going to say 7. Okay. So the next thing that is one of the, I have 20 minutes. Sorry, let me charge my computer. It's about to run the battery. So what we're going to do now is focusing on search algorithms. Oops. is search algorithms. And we're only going to do a few examples of them. There's many other search algorithms, but we're going to focus on sort of what's called depth first search and breadth first search. And the idea is that depth first search kind of go, if I'm thinking about, it's mostly illustrated through a tree, but you can do this over a graph. You go to sort of the deepest possible thing and you traversal. Breadth first search is you look at all your nodes that is one hop away from you, and then look at among all the nodes that is one hop from them. So that is sort of the breadth first search. This is a place where you also can misspell this algorithm many different ways. This is sort of different spelling of this. I mean, they don't really exist, but you can see. And then the most funny one that you would see is the bread first search. So you just go straight to search for the bread. Anyway, let's talk about breadth first search. And then there's a description of the algorithm, and I'm going to run it again through my iPad to show how this algorithm is run. So you start with some node, and then you look at its label, put it in the queue, and then always take the ones that is in queue, find its neighbors, and so on, and perform some operations. So let's do this on the. Okay, so let's do this example here. And we're going to go over this simple example of the breadth first search. Okay, so our starting point is node B. Let's say this is sort of the starting point, and I'm going to kind of do how many steps are there to go from B. And so first of all, I start with B. I look at all its immediate neighbor, A, H, and C. And then what I'm going to do is I'm actually going to mark it to say that, okay, H is one step away from B, A is one step away from B, and C is one step away from B, okay? And what also I'm going to do is I'm going to put it as sort of in a queue where in some order. So I'm going to say A goes into the queue, H goes into the queue, and C goes to the queue, right? This is sort of my neighbor in the first step. And then the current algorithm I'm doing is I'm trying to figure out what is the shortest path between B and G. And then this is me executing my algorithm. So what am I doing? I have exhausted all the neighbors of B. So I'm going to remove B from my current consideration, and I'm going to look at my queue. Then the first queue is A, okay? So now look at A. What is the neighbor from A? Well, the only neighbor of A is B. Well, it's already crossed off. I already take care of it. I don't have to care about it. Same thing with H. I'm looking at H. Well, the only neighbor of H is B. Well, I'm done. Now I'm going to look at C. Okay. When I look at C, the neighbors of C, and when I say done, I'm done processing it. Now the next one is C. C, I'm going to look at its neighbor. So it has two neighbors, as D and E. Because going from B to C takes one step, now from C to D takes two steps. So I'm going to say, this takes two steps and it's coming from C. Same thing with E, it takes two steps and coming from C, okay? So now I've done processing C. But then I'm going to add a new node to the order. So I'm going to say it's D and it's going to E. So since I have already taken care of, well, let me actually cross this out. I've already taken care of A, B, C, and H. The next thing in my list is I want to look at D. So what is happening, D has two neighbors. It has neighbor C and neighbor E. C is already crossed off, so I'm going to look at E. So now going to D to E is one more step. And accumulating from original thing, I'm just going to add 1 to 2 at the beginning. So this is now 3D. What does this mean? This says that, going from D to E takes one step, but then because D already have two steps from B, now getting to E is taking 3 steps from B where the previous node is D. And this is actually where I can stop, because what I have done, because it's a breadth first search, I have already sort of figured out, I have managed to reach the node G with 3 steps. And then this is the shortest path. And I don't have to process the remaining node. And then to recover the shortest path, I'm just going to do backwards traversal. I start with E, G, I go backwards. And because it's coming from D, so I go to D, D coming from C, I go to C, C coming from B, that goes to B. So everything I just drew in purple, this is now the shortest path from my algorithm. Okay? So the last algorithm I want to go through, then we'll move back to, I will move back to the Jupyter Notebook, is what if my graph is weighted? I mean, in this specific case, every single edge is weight 1. So I can do this. And now this is sort of the most complicated version. So let's look at this one. So this one has a more complicated thing, and I think I have time to go over it and move to Jupyter Notebook, and then we're done for the day. So this is try to find shortest path in a weighted graph. And this is the Dijkstra's algorithm, okay? So again, I want to find the shortest path between A and F. And I'm going to use a similar algorithm, except I have to be a little bit more careful of how I am processing the node. So the way I'm going to start doing it, I'm going to start with A. And A has 3 neighbors, B, C, and D. A goes to B, has a weight of 14, goes to C, has a weight of 9, goes to D, has a weight of 7. So again, if you think about the distance it travels, the shortest one is this one. So the way we're going to label it is I'm going to say, well, going from A, I can arrive to D with a weight of 7. I can arrive to C with a weight of 9 and arrive at B with a weight of 14. So this way I am checking what is the next thing in my queue that I need to kind of take care of, but also sort them by distance, because I want to find the shortest path. So I want to start with the shortest one. And now after this, I have finished processing node A. So now I need to process the next several things in my queue, and they are D, C, and B. So I'm going to deal with D first. Now I'm in D, and what are my neighbor? Well, my neighbor A is already removed, so I don't care about it. But from D, I can move to C and move to E. So this is where things become interesting. If I move from D to C, what do I get? I add 10 to my path. So the total path from A to D to C is 17. But I already have C9, meaning that I can reach C using a path of line. So 17 is bigger than 9. So I don't have to take this path at all. So I skip this path. The next one is I can go from D to E, and it's add 15 to 7 right here. So that's 22. So what I'm going to do is to say, well, actually, I'm going to write it also on the graph. This is C9, B14, D7, and I have E22. What I say 22, that means to go from A to E, it has to go through the current path, which is 22. And because it's also the longest path, I'm going to add it right here. So now I am done with D. Okay. The next thing I want to do is C. When I have C, I have 2 paths I can take. Well, it's 3 paths. Well, 4. But if I go back to A and D, I don't care. So I only care about the path that is 2 nodes that I have not visited, and still, I can still visit from C to B. So now this becomes interesting. When I go from C to B, the combined cost go from A to C to B is 9 plus 2, which is 11. What this do, this is actually going to replace, it's actually going to replace this node by a new weight, which is 11, and then it's going to replace this by 11. Okay? Now that takes care of this path. Now C can also go to E. If I do this, then this whole path to E is now 9 plus 10, which is 19, which is better than this path. So again, I'm going to update it to be 19, and happen to be when I'm updating those weights, it doesn't change the order of it. Okay, so now I have processed everything for C. I'm going to remove it from my list. I look at all its neighbors. The next thing I'm going to do is I'm going to look at B. Again, the only one that I want to look for is B can reach F. Everybody else, I have already traversed it. So B to F is 11 plus 9, which is 20. So I'm going to say, well, I can reach F into 20, okay? Well, actually, I'm misleading you a little bit over my labeling. I should always do where the source is on the path. This is coming from A. No, this is coming from, sorry, this is coming from C. This is coming from A. This is coming from A. To follow my traditional thing, the rest doesn't change. This is coming from C. This is coming from B. Sorry, I was doing destination. I should always do the source. So I have done C9. This is A9. Okay, so I've done everything except for the beginning of the queue, which is B11. The only thing I go here is right here. And then F is now reachable through B through a weight of 20. Now the question is, are we done? The answer is actually no, because I actually want to look at the rest of it. So this is the best thing so far, but let's look at whether there's other options left. In this specific case, I might coming from E. So then, oh, actually, I'm also going to add B into this. Oh, no, F into this, which is a node F. And that has 20 in here. So now the next thing I want to process is this piece here. So when I have E can also reach F, okay? But then if I actually reach F, it's kind of cost of 19 plus cost of 6, which is 25. And that is bigger than 20. 25 is bigger than 20. So I don't need to take that path. However, assuming, you know, if I change this weight to be 0.5, then it's totally possible the shortest path is coming from here. So I need to keep going until I process everything in my queue. But in this specific case, when we pass through E19, we decided that, you know, it's not reducing the cost. So E19 is down. Then what we have left is, say, the shortest path is 20 to reach F. How do we get there? We can again trace back, starting from F. It says F is coming from B, so I go back to B. B said it's coming from C, I go back to C. C said it's coming from A, I go through A. So this particular path here, oh, is precisely the shortest path. Okay. Sorry, this is a little bit roundabout, but this is actually how Dijkstra's algorithm works to find shortest path in a weighted graph. So let's move on to the last bit of our. So, well, the shortest path algorithm is part of Network X package. And when you say, okay, in my social network, I want to start with one character, end up in a different character. What are the shortest paths? So it shows the beginning character, end character, and the character is going to pass. But then I can also go from, other two. Oops. And then if I do that, you get the shortest path. This is slightly longer to go from one character to another. And you can probably validate it through the social network visualization we had earlier. And then the one I just spent, at least 8 minutes on is the Dijkstra's algorithm, which is the go-to algorithm to find shortest path in a weighted graph. And this is actually an animation of it. This shows when I'm running this algorithm, how I'm locating my, my next target. And you can see that when it's actually encounters some sort of obstacle, it's going to try to slowly go around it. Okay, with this animation. So the target is that green point. And you can see that, as it's kind of doing this kind of search, it's going to gradually move on to this target point. And once it's reach it, it's do a little bit extra, right? So once it's actually reached that node, it do a little bit extra to kind of be a sanity check. There's no other better path I can find in the local neighborhood. So if I actually look at all the degrees here, and if we run it without weights, this is the path we get before. But if you run it with weights, you will see that the one that with the smallest cost or the shortest path with weights is actually a slightly different path. Okay, in fact, it's actually visited one more character and come back to the major path. And then you can, of course, compute all the relative paths, weights of those paths. You can say, well, in this weighted situation or not unweighted situation, what is the shortest path? In the weighted situation, what is the shortest path? Okay. The last bit I want to describe, I'm not going to super detail, is the A-star algorithm. So A-star algorithm is sort of a slightly smarter way to try to find the shortest path. In some sense, the major difference between A-star and the Dijkstra's algorithm is that it's actually trying to use some heuristics to guide the search into the right direction. And then the main idea is when we actually put the search node into the queue, it's going to try to have what's called the best first search. And it's trying to figure out among all the possible paths, what are the starting position that's going to eliminate or reduce my search space. So the best way for me to show how the difference between these two is against iteration. This is the same sort of space. You start from lower left corner to the upper right corner. This is how A-star works, right? So it's kind of has a reordering how you starting your search, and it's the difference between A-star and Dijkstra is A-star, the moment it finds the shortest path, it actually stops. And in general, it's performed much faster. So finally, I don't have too much time. There's a very important component for graph analysis, which is community detection. And Karate Club is one of those very small, tiny social network where people used at the very beginning. So let's carry the tradition. It's a 34 member in a Karate Club. And then you can do community dash greedy modularity community. This is just a clustering algorithm based on modularity. And then this is sort of the clustering algorithm, but you can actually color them based on, oops, what did I do? Did I forget to run certain things? Yes, let me see. Oh, yes. I forgot to specify the color, of course. Now you can see this is how 3 cluster looks like if I cluster those using modularity-based clustering. There's many other algorithms that is used for social network clustering. You can do the same clustering. In this case, I'm going to cluster into 5 different clusters. And this is how it looks like for the larger social network. Okay, so that's it for today. I know it's fairly dense, but I want to give you a quick overview of how some of those graph analysis and algorithms are done for simple social networks. If you're interested, there is additional reading material under the schedule. So And if you're more interested, my slides actually has more things on graph visualization. And if you're really interested in this, next semester, there's going to be a course over data visualization that is going to cover a bunch of graph visualization techniques out there. All right, so that's it for today. I'm going to stay around for